Hello viewers, welcome to video number 120, and this video number 120 is the 60th episode of Chemical Thermodynamics, where the topic is thermodynamic function of mixing. This is actually the second part where we will discuss entropy of mixing, enthalpy of mixing and volume of mixing. So here is Dr. Mala Das Sharma. So let's start. See, in my last video, I have discussed about this free energy of mixing. Okay, we have derived the expression for free energy of mixing. That means of ideal gases. That means when the two or more ideal gases are mixed, their free energy changed, and the change of free energy, already I told you that the final property, here it is final free energy minus sum of the initial property, that means the sum of the free energy of pure gases at the same temperature and pressure. And we have seen that delta G mixing, this is equal to, that equation is, or expression is nRT summation of xi ln xi. In my last video, I have derived this equation. Now, today's topic is entropy of mixing. Entropy of mixing, that is delta S mixing, right? This entropy of mixing, in my earlier video already I have derived from the total change of entropy of the system, but now we know the expression of delta G mixing. So from this, it will be more easy to derive the expression for delta S mixing. So, entropy of mixing means when of ideal gases, when two or more ideal gases are mixed, then there is a change in entropy, and entropy of mixing will be final entropy, that is entropy of the mixture minus sum of the entropy of the pure individual gases at the same temperature and pressure, right? Now, we'll start from here. So, we know that delta G mixing, that is equal to free energy in the final state, that means after mixing, minus free energy of the initial stage. Okay. So, if we differentiate, so here we will write differentiate with respect to temperature at constant pressure. Okay. Then what it will be? Dole of delta G mixing by dole T at constant pressure, that will be equal to dole GF by dole T at constant pressure minus dole GI initial dole T at constant pressure, right? Now we know that already we derived dG is equal to VdP minus SdT. So if we differentiate this equation with respect to temperature at constant pressure, that is dole G by dole T at constant pressure, that will be is equal to, here it will be constant 0, that means it is minus S. This one already we know. This is this one. So, here what you can write? Dol Gf by dol T at constant pressure, that means that will be minus S final, minus of minus S initial. Okay, we can write. So, next line will be, of course, once again I'll write this first one. Dol of delta G mixing by dol T at constant pressure, that is equal to what we found? Dol Gf by dol T at constant pressure minus dol Gi by dol T at constant pressure. So, here I can write it as this is minus F minus of minus SF, that means entropy in the final state, minus of minus Si. So, this is equal to minus delta S, and delta is change in entropy of what? Mixing of ideal gases, that is minus delta S mixing, right? So, therefore, minus delta S mixing, that is equal to dol of delta G mixing by dol T at constant pressure. Okay. So, from here what we can write? Delta S mixing, that will be is equal to minus, what is delta G mixing? Delta G mixing is dol of, we know that it is nRT, then summation of xi ln xi. Okay, xi is, what is xi? Xi is the mole fraction of the ith component. Just I rub it. Acha. Mole fraction of the ith component. Okay. Then by dol T at constant pressure. Can write it. Now you see, we have to differentiate with respect to temperature. Okay. Here, this N R number of moles, then R and then Xi, that is mole fraction, all are independent of temperature. Okay, at constant pressure. And so here it is, what is left over? ddt of T. Right? ddt of T will be equal to 1. So what will be the final answer? Final answer is delta S mixing, that will be is equal to minus nR summation of xi ln xi. This is the expression of delta S mixing, or this entropy change during the mixing of ideal gases. Now look at here. This xi is less than 1 because total mole fraction will be 1. So mole fraction of any component will be less than 1. So ln xi, okay, it is less than 1, that will be negative. So negative, here it will be positive. So therefore, we can write, therefore, delta S mixing, this is your positive. Okay, delta is mixing positive means the mixing of ideal gases is a spontaneous process. Okay, because for spontaneous process only entropy change is positive. Acha. In my last video, we have seen that delta G mixing that has come out, it is negative. So delta G, change of Gibbs free energy negative means that process is spontaneous. So this also proves that mixing of ideal gases is spontaneous process. So therefore what we can write? Therefore mixing of ideal gases is spontaneous process. Okay. So because delta is mixing positive, delta G mixing negative. So it is a spontaneous process. Achha. Now just like this earlier video where we have derived completely the delta G mixing, just like that here also if you take two components, any two component system, then delta S mixing that will be is equal to minus NR, then what it will be? X1 ln X1 plus X2 ln X2, only two component, and X1 and X2 are the mole fraction of component 1 and mole fraction of component 2. So exactly in the same way you can derive that this delta S mixing, okay, this one will be maximum, it will be maximum, okay, it will be maximum at x1 is to x2 is equal to 1 is to 1 or x1 or x2 is equal to 0.5. Okay, in the same way you can derive, as you just refer my earlier video, same calculation, same derivation, we can derive that here this delta S mixing is maximum at x1 is to x2 is equal to 1 is to 1. Here it is maximum. In case of delta G mixing, it was minimum. Okay, and value is x1 is equal to x2 is equal to half or 0.5. So this is the curve. Okay. Next, now we'll go for this enthalpy of mixing. Next topic, enthalpy of mixing. Right? Enthalpy of mixing means that is delta H mixing. We can denote it like that. Okay. Now it is very simple. We know that delta G is equal to delta H minus T delta S. Right? So what we can write? Delta G mixing is equal to delta H mixing minus T delta S mixing. Okay. So from here what can I write? Delta H mixing that will be is equal to delta G mixing plus T delta S mixing. Now just to put the values of delta G mixing and delta S mixing, what we will get? Delta H mixing or enthalpy of mixing is equal to delta G mixing is nRT summation of xi ln xi, right, plus delta S. Delta S means minus nR, T is already there, then summation of xi ln xi. Just now I have derived. Okay. So, these are same. That means this is getting cancelled. So, delta H mixing, that will be is equal to 0. So, there is no enthalpy change during mixing of ideal gases. So, no enthalpy change during mixing of ideal gases. Okay. So, delta H mixing is equal to 0. Now, coming to the last topic, that is your volume of mixing. Volume of mixing, or it is delta V mixing. Right? Now, once again, we know that dG is equal to VdP minus SdT. Right? Now, if you differentiate with respect to pressure at constant temperature, then this will be is equal to V. Okay, constant temperature, so this part will be 0, it is V. Right? So, now, this is your V. So, delta V mixing, what will be delta V mixing? Delta V mixing, that will be is equal to dole of delta G mixing by dole P at constant temperature, right? Now we'll put the value of delta G mixing. So, delta V mixing is equal to dole of, this is nRT summation of xi ln xi by dole P at constant temperature. Now look at here. This N, R, T, Xi all are independent of pressure. So this differentiation value will be 0. So this will be is equal to 0. Why? Because all this term, that is N, R, T and Xi, these are independent of T is, anyhow, T is constant, R is also constant, then your N, Xi, these things, they are independent of, anyhow I have written, but R and T are constant already, independent of pressure. So, this derivation is 0. That means, what is the conclusion? during mixing of ideal gases, there will be no volume change. So we'll write the conclusion. 1 minute. So we'll write the conclusion. That is, therefore, during mixing of ideal gases, no volume change occurs. Okay, so this is the conclusion. Now one more thing you remember, all these relations or all this equation, delta G mixing, that is free energy of mixing, entropy mixing, enthalpy mixing, volume mixing, all these equations are also valid for ideal liquid solutions. Very important. Remember, note it down that all these equations or relations, whatever it is, all these equations are also valid for ideal liquid solution. Ideal liquid solution. Ideal liquid solution. Okay, remember this point. So we have come to the end. We have derived the expression for free energy change of mixing, and today we have seen that we have derived the expression for entropy of mixing and then enthalpy of mixing, which is 0, and also volume of mixing, which is also equal to 0. Hope you have understood. Thank you.